Welcome back to the deep dive. Today, we're going behind the curtain a bit. We're looking into the world of AI infrastructure. We hear constantly about these amazing AI models, what they can do, but what's actually powering them,
Yeah.
what makes it all possible. That's what we want to unpack today.
hmm
And our source material for this one is, well, it's pretty unique. We've been looking at an exam review, actually.
An exam review.
Yeah, for the HPE2-B08 exam.
Yeah.
All about AI infrastructure and solutions. Sounds maybe a bit dry, right?
A little bit, maybe on the surface.
But looking at it through these practical questions, it's surprisingly revealing about how this stuff is actually engineered. Really informative.
That's absolutely right. And our mission, really, is to pull out the critical bits of knowledge, about building and managing these really robust AI systems. We're using these questions as a sort of lens to break down the core parts, what they do, and crucially, why they're so essential for AI workloads. So we're turning the technical stuff into hopefully clear, understandable insights for you. The source is an exam review, context like web-based, 1 hour 30 mins, 40 questions, 70% pass mark English. But forget the test itself. Our focus is purely on the knowledge, the foundations.
Okay, let's dive in then. Foundational hardware. When you think about serious AI computation, especially, loading up with GPUs, what kind of system are we actually talking about? Is it just a standard server with extras or something else?
That's a great starting point. For those really high-density GPU setups, you really do need something purpose-built. We're talking about systems like the HPE Apollo 6500 Gen 10 Plus. Now, this isn't just your everyday server with a few extra slots bolted on. It's specifically engineered for compute power and, importantly, scalability. It supports packing multiple GPUs into one chassis. And the key insight, AI training, especially big models, it needs massive parallel processing. This kind of server delivers that efficiently.
Right. You need the right chassis for all that horsepower.
Mm.
Makes sense.
Yeah.
But okay, once you have all that hardware, the servers, the storage, networks, it sounds complex. How do you actually manage it all effectively? How do you orchestrate it?
That's the million-dollar question, isn't it? And that is exactly where HPE OneView steps in.
Yeah.
Think about trying to manage everything separately. Server console here, storage tool there, network thing over there. It's messy.
Yeah, sounds like a headache.
OneView simplifies all that. Its main job is unified automation. Compute, storage, network resources, all managed together. So the insight is really about shifting from reactive management to proactive automated control, which is just essential as AI infrastructure grows. It means faster deployment, better resource use, huge for AI projects.
Okay, unified management, got it. So we have the power, we have the control, but AI runs on data. Massive amounts of data.
Yeah.
How do you ensure that those huge data sets are, well, not just stored, but accessed really efficiently? Especially if you're building, say, a private cloud. Speed matters there.
Oh, absolutely. Think of your GPUs like Formula One engines.
Yeah.
Super fast. But if the fuel line your storage is slow or inconsistent, the engine just sits there, idling,
Right.
starved.
Bottleneck.
Exactly.
Right.
So in a private cloud AI setup, the absolute must-have for storage is high throughput and low latency. AI training needs fast, constant access to big data sets. This kind of storage ensures the data pipeline keeps up with those hungry GPUs. It makes a massive difference to training speed and efficiency. It's surprising how often slow storage is the real performance killer, leaving expensive GPUs just waiting.
That's a great analogy. Okay, so speaking of those GPUs, we've talked about packing them in. But how do you get the absolute most out of each one? Is there a way to make them more efficient? Because sometimes you might have huge GPU, but maybe only a smaller task needs to run on it. Seems wasteful.
That's a very common scenario, and yes, there's a clever solution for that. It's the NVIDIA MIG feature. That stands for Multi-Instance GPU.
MIG, multi-instance GPU.
Okay, so what it does is it lets you partition a single physical GPU into multiple, smaller, totally isolated instances. Each one acts like its own independent, smaller GPU.
Ah, interesting. So you can carve it up.
Exactly. This means much better utilization. You can run multiple users or different smaller workloads all at the same time on one physical card without them interfering with each other. It's a game changer for utilization and, frankly, for cost effectiveness. You're not wasting cycles on those big, expensive GPUs. Really crucial insight for managing a fleet of them.
Virtualizing the GPU itself, essentially. That's smart. Okay, moving up a layer.
Yeah.
Beyond the individual components, how do organizations manage the whole AI or machine learning workload, especially at scale?
Yeah.
Particularly with containers becoming so common. What software pulls that all together?
Yeah, you definitely need a software layer for that kind of orchestration.
Right.
Think of your AI applications packaged up in containers, like little self-contained units. You need something to manage deploying them, scaling them, making sure they talk to each other correctly. That's where HPE Ezmeral comes in.
Ezmeral. Okay.
It's a software platform. Its job is orchestrating those containers, managing Kubernetes clusters. Kubernetes is like the conductor for all these containerized apps, and generally running those AML workloads at enterprise scale. It streamlines the whole process, making it easier to deploy and scale complex AI applications.
Makes sense. You need that higher level coordination. Now, something absolutely critical, often maybe overlooked until it's too late, is security. How can you be truly sure your AI infrastructure is trustworthy right from the very start? Like, how do you know the hardware itself hasn't been messed with?
That's a fundamental security concern, and it starts right at the hardware level. This is where the HPE silicon root of trust is so important.
Silicon root of trust.
Yes, it's hardware-based security, baked right into the silicon. What it does is validate the server's firmware, the really low-level software during the boot process. It checks that nothing's been tampered with. So it protects against firmware attacks, ensures you're starting from a known, trusted state. It's like checking the foundation before you build the house.
Okay, hardware level guarantee. That's reassuring. Now, let's think about resource allocation again. If the main CPUs are churning away on the AI math, what about all the background tasks, like handling the network traffic, managing storage access? Does that bog down the CPU?
It certainly can, and that's precisely why you might use something like NVIDIA Bluefield DPUs. DPU stands for Data Processing Unit.
DPUs. Okay, different from GPUs and CPUs.
Right. These are specialized processors. Their whole job is to handle networking and storage tasks, offloading them from the main CPU. Think of it like giving data transfers their own dedicated fast lane, separate from the main compute highway.
Ah, okay.
This frees up the CPU cores to focus purely on the AI calculations. The result, better overall performance, lower latency for data movement, really helps optimize the whole system.
Speaking of low latency and data movement, you mentioned dedicated lanes. What's the key networking tech for those really critical AI data pipelines where you need data to fly between storage and compute?
For that ultra-low latency communication, the technology you often see is RDMA over Converged Ethernet, usually just called RoCE.
RoCE, got it.
RDMA means Remote Direct Memory Access. So RoCE lets systems access memory directly over standard Ethernet networks, bypassing a lot of the usual software layers. This drastically cuts latency and reduces the CPU overhead needed for data transfers. In AI, where you're constantly moving data between storage and GPUs, this efficient communication is just paramount. It keeps everything flowing smoothly.
Like an express lane for data between components.
Okay, now practicalities. These are complex systems. Things can go wrong. What if a server hangs or the OS crashes? How do you manage it remotely if you can't even log in normally, especially if you're not physically there?
That's a very real scenario, and the solution is typically something called HPE-IO, which stands for Integrated Lights Out.
ILO, yeah.
So we'll call an out-of-band remote management tool. That means it works independently of the main operating system. So even if the server OS is completely dead or unresponsive, administrators can still remotely access the server, monitor its health, power it on or off, troubleshoot, basically manage it.
Ah, like a separate little management computer built in. Essentially, yes. It's crucial for maintaining uptime and fixing problems quickly without needing someone to physically go to the data center. A lifesaver for remote management.
Definitely sounds essential.
Yeah.
Okay, so we've covered a lot of ground from servers to software to networking and security. Let's pull it all together. When we talk about the absolute bleeding edge, the truly massive AI models, think large language models with billions, maybe trillions of parameters, what kind of infrastructure actually handles that level of scale?
Right. When you get to that extreme scale, you're often moving beyond even clusters of standard servers. The scenario that really fits deployment for those massive cutting-edge models involves systems like HPE Cray-EX with GPU acceleration.
Cray, okay, that's supercomputing territory.
Exactly. These aren't just bigger servers. They represent a different architectural approach altogether. They're designed from the ground up for extreme scale, high-performance computing. They focus heavily on interconnects, minimizing communication bottlenecks between thousands of processors or GPUs at a scale traditional systems just can't handle. That's why they're indispensable for training those giant models that need just immense compute power and memory and incredibly fast internal communication.
Wow. So it really is a whole spectrum of infrastructure depending on the scale and complexity of the AI task. We've talked about today the servers, the software, the networking. How will they need to change and innovate even further to keep up? What new challenges pop up when we think about even greater scale? And how do these building blocks pave the way for whatever comes next in AI? Something to think about.